In this video, we'll review reactions of carbohydrates. So first of all, let's review oxidation. What does oxidation look like? Well, this looks like the conversion of the aldehyde in D-glucose to a carboxylic acid, like gluconic acid. So let's look at this. We've got glucose, and it's a D-glucose, so it's CH2. And then the very next C has OH on the right. That's what makes it D. And then if we go up to the next C, there's OH on the right, and then to the next C, OH on the left, and to the next C, OH on the right, and then we end in C, double bond O, and an H. So there is our aldehyde. And remember, this is an aldose. It ends in OSE because of that aldehyde. So we would classify this as an aldose. It's got 1, 2, 3, 4, 5, 6 carbons. So this is a hexose, just for good review. If we combine this with 2 equivalents of copper 2 plus blue, so our Benedict's reagent, and in the presence of base, we can convert this to a carboxylic acid. So we convert the aldehyde at the end of glucose to a carboxylic acid. We oxidize it. And recall that in organic chemistry, oxidation is really about having more bonds to oxygen. So oxidation really looks like increasing our number of CO bonds. We'll also find that we're decreasing the number of C to H bonds that we have. So on our aldehyde, we used to have this C to H bond connecting the C double bond O, C to the H. We've got one less bond there. And we've got one more C to O bond when the C ends up bonded to not only double bonded to an oxygen, but bonded to the O in the OH to make the carboxylic acid. So that's oxidation in organic chemistry. Is there loss of electrons going on as well? Sure, but it's just not what we focus on. And then the product, this copper 1 oxide is actually what's been reduced. Well, the carbon gets oxidized. It's actually this copper going from 2 plus to plus 1 because our O is a 2 minus. It's our copper that's been reduced or is our oxidizing agent. So here's our ox agent. It itself has been reduced from 2 plus to a plus 1. So could we follow loss of electrons and gain of electrons? Sure, we could. But in organic chemistry, we tend to just look for those more bonds to oxygen. Okay, so in this example, our copper 2 plus in our Benedict's reagent is our oxidizing agent. In your body, it would be a biological oxidizing agent. Usually we have enzymes functioning and doing these. All monosaccharides can get oxidized. All monosaccharides, therefore, are reducing sugars. The idea is that the Benedict's reagent has been reduced. Who did that? The sugar. So if the Benedict's is the oxidizing agent, the glucose is our reducing agent. And so therefore, it's a reducing sugar. All monosaccharides give a positive Benedict's test. Most disaccharides can get oxidized. Sucrose is the exception. Sucrose cannot get oxidized, but most disaccharides can. Most disaccharides, therefore, are also reducing sugars. And again, the exception is sucrose, which is not a reducing sugar. Most disaccharides will also give a positive Benedict's test. The exception is sucrose, gives a negative Benedict's test. Polysaccharides are just way too big. They get hydrolyzed, eventually becoming glucose. Okay, at this point, you may be asking yourself, well, how is it though that all monosaccharides are managing to get oxidized? What about the ketoses? I mean, those contain ketone functional groups. How are we oxidizing those? Well, here's the thing. These ketoses are kind of unique. These ketoses are kind of unique in that they can get rearranged. Essentially, they isomerize. So let's start off here with, let's say, D-fructose. We're going to be able to lead into D-glucose from there. So it's going to start off the same. At the bottom, we'd have CH2OH. And then here would be our chain, and we would have OH on the right. We're just drawing a straight chain backbone with an OH on the right, and we'll do another OH on the right. And then we'll have OH on the left as we go up the chain. And then we'll have a C double bonded to an O to be the ketone. And then, of course, I'm going to run out of room. But then we'll do CH2 and an OH at the top of the chain. So you might be asking, well, how on earth did they get oxidized? Well, in these basic conditions, they are able to isomerize, or, essentially they get rearranged through this, equilibrium in basic conditions where they're in equilibrium with the aldehyde form, so that D-fructose essentially converts to D-glucose. So the ketone essentially is able to isomerize basically through that ring form, but it's we won't get into it at this point. But it's basically able to convert from this ketone to its aldehyde form, and then it's the aldehyde form that gets oxidized. So the ketoses convert to aldoses. So it really goes ketose to aldose. That's then able to be converted to that carboxylic acid. Through oxidation. Okay, so what about redox? Well, what about the reduction side of the redox? What does reduction look like then? It would look like, okay, by the way, let's address this. This does not generally happen in your body. It is a reaction that is used in the food industry. It's used in the food industry to make sugar alcohols. These sugar alcohols are sweet, but they don't promote tooth decay, don't cause the large, swings in blood sugar levels that sucrose does. So these are what we think of as some artificial sugars like sorbitol. So how are these sugar alcohols actually produced? Well, let's look at this reduction. Here we have a beta D glucose, and it's in its ring form, essentially. So we've got our six-membered ring where oxygen is one of those carbon, taking up one of those places in the ring in place of a carbon. And then from that oxygen, the next carbon has an OH up, and the next carbon has an OH down, and the next carbon has an OH up, and then the next carbon has an OH down, or like every other. And then the next carbon actually has CH2OH. So sugars like glucose in their ring form are in equilibrium with their straight chain form. There's more of that ring form in aqueous solution. But they are in this equilibrium back and forth with their straight chain form. And so next we have our straight chain form of D-glucose, CH2OH, COH on the right makes it D, and then COH, and then C on the right, and then COH on the left, COH on the right, and then C double bond O with an H. And it's actually in the straight chain form, though, that this reaction can occur. And it's hydrogenation, and it's very similar to hydrogenation we've seen before, where we're adding hydrogen really across a double bond, and that double bond's the aldehyde double bond. Adding hydrogen, across the C double bonded to the O, so that you end up with, instead of the C double bonded to the O, the C has one more bond to hydrogen, and then the O has a bond to hydrogen, making an alcohol where we used to have an aldehyde functional group. So we need hydrogen and the presence of a catalyst. We have palladium listed here. I thought that they use nickel more in industry. I think that's cheaper. So maybe it's palladium, platinum, nickel. These metal catalysts act similarly. And then it's going to reduce that double bond to single bonds to hydrogen. So what does organic reduction looks like? Well, it looks like we're going to take our number of carbon to oxygen bonds and decrease them, and take our number of carbon to hydrogen bonds and increase them. That's organic reduction in general. And so this is how sugar alcohols are made in industry. So this produces what's called glucitol or sorbitol, it's known as. And so this is how, we industrially make sugar alcohols. It's not really a biochemical pathway, it's an industrial chemical, biochemical reaction. And so it's something used in the food industry, for the sole purpose of making these sugar alcohols as sweeteners, as sugar alternatives. And so it's called an alditol, where it has an OH group on every single on all 6 of the carbons, really. So alditol is like calling something an aldose or a ketose. This is an alditol because of all of those alcohol functional groups that are on it. So just to review, we can form sugar alcohols from monosaccharides when we reduce monosaccharides down to these primary alcohols. We'll end up with a primary alcohol when we reduce this aldehyde, and we're using hydrogen and a metal catalyst to do the job. Next, let's review condensation. Condensation looks like taking 2 smaller molecules, putting them together to make a bigger molecule with the loss of water as a product. Okay, so all carbohydrates, monosaccharides, disaccharides, and polysaccharides can undergo condensation. This is a way to essentially polymerize or to, make chains of molecules. So in our first example here, we've got our 6-membered ring carbohydrate where an oxygen is one of those spots in the ring. Now, labeled as carbon 1 in the ring is called a hemiacetal. That is a carbon that is both connected to an alcohol and, is also connected to an ether functional group right beside it. So what that really means is that carbon on the ring, it's called carbon 1. And then there are, 4 more carbons. So there's 5 total carbons in the ring. The 6th spot is the oxygen of the ether in the ring. And the carbon 1 is connected to the oxygen ether carbon, or excuse me, the oxygen ether position. And then it's also connected to an OH. Now in the next ring, we've just got a repeat of the exact same ring, but at carbon 4, there's an OH. Okay, so it's really the OH of the hemiacetal that's going to react with the H on carbon 4 of the opposite ring, that's going to be your loss of water. It's going to be this H and this OH that are together going to make water in the product side. And look out for that hemiacetal, that carbon 1, because that becomes what we call our glycosidic linkage. That's really important. We want to look for that glycosidic linkage, that special new bond that's formed that holds those two rings together. So it's really the carbon at carbon 1 of the hemiacetal connected to the oxygen of the next monosaccharide. And this is the general structure of a disaccharide. We hear a lot about these, about sugar in everyday life, so that's important. A disaccharide is going to have that glycosidic linkage. It came right from that hemiacetal carbon of one of the rings, one of the carbohydrate rings. Okay, what's hydrolysis? Hydrolysis then is just the opposite. In hydrolysis, we're going to cleave that glycosidic linkage. We're going to break it. We want to cleave the glycosidic linkage. So we've got an example here of a disaccharide maltose. Okay, so as we go around the maltose ring at carbon 1, we see that that was our glycosidic linkage carbon. Then at carbon 2, there's an OH down. At carbon 3, there's an OH up. So that's carbons 2 and 3. At carbon 4, there's an OH down. At carbon 5, there's CH2OH connected to it. So that'd be our 6th carbon. And then in the opposite ring of maltose, at carbon 1, we have OH down. At carbon 2, we have OH down. At carbon 3, we have OH up. At carbon 4, we're connected to our maltose, we're connected to our oxygen that's connected to the other ring, or has got the glycosidic linkage. And then the next carbon, or the last one, has CH2OH going up. And then, of course, the oxygen is in that 6th position. Here, we're going to cleave that glycosidic linkage, and we're going to add water. So we're going to add H on one side and OH on the other. So we're going to need OH on that first molecule, on that hemiacetal or carbon 1 is going to need the OH group to add. And so we're going to break or cleave right here. We're going to have to add OH here, and we're going to have to add H on the right side. So water is added H on one side and OH on the other. So we started off with maltose, a disaccharide. We added water. We cleaved the glycosidic linkage between the two carbohydrate monomers, and then we ended up with 2 identical molecules of glucose. So maltose is, hydrolyzed in hydrolysis into 2 of the glucose monomers. We also needed an enzyme to catalyze the hydrolysis. So, for example, in the case of maltose, we need maltase as an enzyme catalyst. Remember that we had a matching catalyst for essentially each of these disaccharides, and maltose needed maltase as its enzyme catalyst to undergo the hydrolysis. Monosaccharides can't undergo hydrolysis because what would you split? There's just one of them. But all your disaccharides and all your polysaccharides, they can all undergo hydrolysis. So we're really looking for that glycosidic linkage and looking to break that glycosidic linkage in order to do hydrolysis.